In 4.5, we look at two things, basis and dimension. And in a previous video, I mentioned briefly a little bit about basis. But basis is basically a set of vectors that can be used to describe anything in that vector space. For example, the vector space R2 is a set of all vectors that are two-dimensional, where x and y can be anything, so that's our vector space. And we have seen previously that the two vectors 1, 0 and 0, 1 span R2. Any vector in R2 can be written as a linear combination of 1, 0 and 0, 1. So these two span R2. Also, these two vectors are linearly independent. We only have two, so one is not a scalar multiple of the other one, so they're not dependent, therefore they're independent. So in order for something to be a basis, it must span that vector space, and all of the items in that set must be independent. So this is said to be the standard basis of R2. Now, we demonstrated before that there are other bases of R2. We've seen other examples of vectors that we could use to combine and form a basis. For example, in another video, we saw how 2, 1 and negative 1, 2, we've seen that they span R2, that any vector x, y could be rewritten as a linear combination of the first vector and the second vector. And we found out exactly how they were related to x and y. These two are linearly independent. So since they span R2 and they're independent, this forms another basis for R2. So while we have a standard basis, there are lots and lots of different bases that could be written to span our vector space and that are also independent. Now, when we refer to the idea of dimension, dimension is just how many vectors does it take to form our basis. So for R2, notice both of our spanning sets had two elements in them. So the dimension of R2 is 2. If we were to add another vector to either one of these sets, it turns out that other vector would just be a linear combination of these two, or in this case, these two, so that set would no longer be independent, so it would not be a basis. On the other hand, if we were to omit one of the vectors, for example, in the first set, if we omitted that one, we can't form every possible vector using just this one. Or in the second set, if we omitted that one, we couldn't form every possible vector using just this one. So adding an extra vector makes it not independent. Taking one away makes it not span. So no matter which particular basis we use, the basis will always have the same number of elements in it. So the dimension is just a way of quantifying how many elements does it take to form a basis for that particular vector space. So in this one, for R2, it takes 2. If we want to look at R3, the standard basis for R3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. Because with those three vectors, we can form any other vector we want. If we want to form the vector 5, 7, negative 2, I would just need 5 of these, because that would give me 5 for the first element. 7 of these, that would give me 7 for the second element. Minus 2 of these, that would give me a negative 2 for the third element. So these three vectors span R3. They're linearly independent. So this is our standard basis for R3. So the dimension for R3 is 3. That's the number of vectors required to form our basis. If we took 2 away, it would no longer span R3. If we added another one, it would simply be a linear combination of these 3. So it would no longer be independent. So 3 is the exact number for our basis. So if you're ever given a set and asked, could this set possibly be a basis? So if I want to know, is this a basis for R4? Is this set a basis for R4? No. This could not possibly be a basis for R4 because the standard basis for R4 has 4 vectors in it. So if the standard basis has 4 in it, then all bases have to have 4 elements. So if this one doesn't have 4, then this couldn't possibly be a base for R4. So those are the 4 standard, or this is the standard basis. Those are the 4 standard vectors that would span R4 and that are linearly independent. Let's see. Let's look at another example. We look at this example 1, 0, 1, 1, 1, 0, 0, 1, 1. If we want to see if this could possibly be a basis for R3, then we would want to check 2 things. Are these 3, do they indeed span R3? And are they linearly independent? So in order to span R3, if we take those 3 and add them together, can we get any possible vector in R3? So if we have A times the first one, B times the second one, C times the third one, could we get any possible vector? So if we set up that augmented matrix, 1A1, well, let's write the equations out first. 1A1, or 1A plus 1B plus no C's equals X. No A's plus B plus C equals Y. 1A plus no B's plus C equals Z. So if we look at that augmented matrix, we have 1, 1, 0, X, 0, 1, 1, Y, 1, 0, 1, Z. So let's work through this and see, is there a solution here? Do these, in fact, span? So we have a pivot here, we need a 0 underneath it, so let's take the opposite of R1 plus R3 to get our new R3. So 1, 1, 0, X, 0, 1, 1, Y. Negative 1 plus 1 is 0. Negative 1 plus 0 is negative 1. 0 plus 1 is 1. Negative X plus Z. So we have a pivot there, 0's underneath it. We have a pivot there, so we need a 0 underneath that. So let's add R2 and R3 together to get our new R3. So we leave the first two the same. So if we add row 2 and row 3 together, we get that. Of course, we can get a 1 here if we divide the third row by 2. So if we divide this by 2, we get a 1. Divide that by 2. We could put it in reduced row echelon form and find out exactly what A, B, and C are. But notice we have a pivot in all of these. So there is a solution to this. Hence, these three vectors span R3 because we can get any vector. You tell me what X, Y, and Z are, I'll tell you what A, B, and C would need to be to get those particular vectors. So, do we span R3? Yes. Are these three vectors linearly independent? Remember we said the way we check that is we set up the homogeneous, we add them together and see if that equals 0. If the only solution to that is the trivial solution, then yes, they are linearly independent. So if we change all of these to zeros, that means these would all be zeros. Which means these are zeros. This last row says that C equals 0. This says that B plus 0 equals 0, so B equals 0. This says A plus 0 equals 0, so A equals 0. So the only solution to this is the trivial solution. So are they independent? Yes, they're independent. So since these three vectors span R3, and since they're independent, then they do form a basis for R3. It's not the standard basis, but they do form a basis for R3. Any vector can be formed out of those three, and they're independent. So that's the minimum number and the maximum number required using those particular to form or to span R3. So that's our basis. So our dimension, don't forget, is 3. 1, 2, 3 vectors is what's required to span our particular vector space, R3. So whether it's a polynomial, whether it's a matrix, a vector, if we're wanting to check to see if something is a basis, does it meet these two criteria? If we're given a set and we want to know, is it possible that it's a basis, then we need to think about dimension. And we know that for any particular space, if we already know the dimension of it, then if a set has more or less than that particular number, it can't possibly form a basis. Because either the set will be dependent or it won't have enough to span our vector space. So just some things to think at as you're working through some of these homework problems.